The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Problem 11 states that a string is wrapped around the periphery of a 5 centimeter radius cylinder free to rotate on its axis. If the string is pulled out at a constant rate of 10 centimeters per second, it does not slip on the cylinder. The angular velocity of the cylinder in radians per second is blank. So, draw out our situation. We just have a cylinder on an axis, which you can assume is in the center unless they tell you otherwise. And we have a string wrapped around it that we're pulling out at a constant velocity, or constant rates, which hopefully by now, rate means the same thing as velocity. Anytime you see constant, you should definitely pay attention to that. That makes life a little bit better because there's no acceleration. We know the net force equals 0. A lot of concepts come from a constant velocity situation, so definitely key here. So we know the velocity it's pulled out at is going to be equal to 10 centimeters per second. And they gave us the radius as r equals 5 centimeters. Now, they want an angular velocity. They want the angular velocity of the cylinder. Now, if there's no slipping, that means that the outside of the cylinder is actually moving at the exact same rate as the rope, which is a big concept in this class. So no slippage means wherever the rope is in contact with whatever's rotating, they actually have the exact same linear velocity, your v variable. So we know the outside of the cylinder at any point has a velocity equal to 10 centimeters per second as well. Okay. Now once you know the velocity of a certain part on a rotating object, then as long as you know the radius from the center of rotation to the location of the velocity, then you can solve for the angular velocity. So we know our equation v is equal to r omega. Okay. Now we know our radius is 5 centimeters, and we know the velocity at that radius is 10 centimeters per second. So we can say 10 centimeters per second equals 5 centimeters times omega. Now I wrote out the units here because if everything's in the same units, sometimes you can actually leave those units in as long as you keep track of them and make sure they cancel out. So when we divide through 10 centimeters per second by 5 centimeters, that's going to be equal to omega. The centimeters actually cancel, and what you're left with is basically inverse seconds or radians per second. Radians are unitless, and as long as you use this formula correctly, which we just did, then you're going to end up with units of radians per second. So our omega is going to be equal to 2 radians per second or 2 inverse seconds, depending on how what professor's talking to you. Basically, I've heard it both ways from different professors from different colleges. This is our answer. The good news is you don't even have to worry about which units they want because they actually just give you numbers. So this is how you solve the problem. Pretty much a straightforward angular kinematics problem, rotational kinematics.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.